Revisiting this question where we've got an arrow on Earth launched at an angle theta and a speed v, a launch speed v, and we're going to relaunch that same arrow with the same angle and same speed on the moon. And we want to compare how high the arrow goes on Earth compared to how high the arrow goes on the moon. Now this last method uses a method where we get the equation, we isolate all the constants, and by that I mean what's the same on Earth and the same on the moon. And once we have that equation, we've got all the constants isolated, we can set up kind of a before and after equation, almost like a ratio. So I've kind of cut to the chase in this question. My initial speed I'm saying is v, there's my angle theta, and I'm looking for h. So as usual, I set it up in my x and y direction. Vx is just v cos theta according to my picture here, right? The x will be the cos. V initial in the y is v sine theta. The final velocity right at the peak in the y is 0. That's what defines the maximum height. And we're going to say my acceleration is negative g, which is true on the Earth and on the moon. They just have different g values. And we're looking for h. So we're going to choose to focus on the y column. We don't want to put an equation with t in it because that introduces another variable. So we're going to pick an equation that has the ability to find h without time in it. And the only equation that doesn't have time in it is this one. V final squared is V initial squared plus 2AD. So putting in our values, staying within the y column, I get 0 squared because my final velocity vertically is 0, is V initial squared. Now we said V initial was V sine theta. Notice it's all in brackets and we have to square that. And then I just sub in. 2 stays, but acceleration is negative g. And we're going to solve this equation for h. So when I do that and do a little bit of algebra, I get h equals v sine theta all squared all over 2g. Now, constants, what's the same on the Earth and on the moon? Well, we said the launch speed was the same, so v is the same, the angle's the same, so obviously 2 is a constant. So I'm going to put the things that change in blue. So the height the arrow will travel will change, and gravity, of course, changes on Earth compared to the moon. So all this yellow stuff is the same, both on Earth and on the moon. So let's solve this equation. Let's get all that yellow stuff, v sine theta all squared divided by 2 by itself. And I end up getting this. I get the product of h times g is going to be equal to this constant. Now, it doesn't matter what that constant is. Let's just call it a constant. Hg is always going to give us the same number whether we're on the Earth or the moon because v sine theta is always the same. So that means the product of hg on the Earth is going to be the same as the product of hg on the moon. So if I write one last little formula where I go h Earth, so I'm going to use an e, times g Earth, that has to be the same as h moon times g moon. Now we know that g moon is simply g Earth over 6. 1/6 that of the Earth. Plug that in. And I get h Earth g Earth equals h moon. And wherever I see a g moon, I'm just going to plug in g Earth over 6. Now notice I've got a g Earth on both sides, so those cancel, and I'm left with h Earth is h moon divided by 6. Or, if I solve that for h moon is 6h Earth.